All right, it's 11 o'clock here in Europe, so let's move on with the next presentation from Be Green by Vladica Sark from IHP Microelectronics. The floor is yours.
So thank you very much, Hank. And thank you for the introduction. So today I'm gonna do a presentation on behalf of the project Be Green, and this project is focused on many aspects, and I'm gonna do just a presentation on the ISAC aspect, which is also included in this project, but this is just a small part of the project, so it's not the whole story. And therefore, the title of this presentation is ISAC for Improving Network Energy Efficiency. And I'm gonna also present some implementation which we did and initial results. So this is the outline of the presentation. I would introduce the project. I would give the motivation for this project, would talk about the scope and objectives of the project. And yeah, later I would talk about ISAC for improving the network energy efficiency, some initial implementation and results, and finally the conclusion and the future work. So the Be Green project, the title of the project is actually Beyond 5G Artificial Intelligence Assisted Energy Efficient Open Radio Access Network, is SNSJU Phase 1 project. The stream is green radio technology. The duration is 30 months, and we end up around 20. We are in the around 20th month, so basically we have 1/3 of the project duration left. We have 12 partners, if I'm not wrong, most of them industrial, and a few academic partners, which are listed here. In the interest of time, I would not go through all of them. So what is the motivation? The motivation for this call or for this stream is basically the climate change. So in this plot here, we can see how the carbon emissions are developing starting from year 1900 till 2016. So I don't have the last almost decade, but nevertheless, we can clearly see that we are actually introducing quite high carbon emissions, and the trend is growing. So it's given by the continent, and we can see that all the continents are contributing quite a lot. What is interesting this bluish line, and this is actually the temperature variation over this period of time, and we can see that we can easily see that it follows actually these carbon emissions, which are human-induced emissions. Most of the scientists believe that this temperature variation or increase is due to the human activity. There are some small group of scientists which believe that this is not the case. I'm not getting into that, but the thing is that the common understanding is the stakes are too high not to address this issue. So basically, this project goes to address this issue for the mobile communication industry, and basically the telecom actually consumes 2 to 3% of the total energy consumption in the world. And we can argue that, yeah, this is not too much, but if you look into the other industries, the figures are more or less the same. So there is no a single industry which is consuming like 30% or 50%. The figures are all the same. So that means that we need to address all of these industries separately and try to reduce this footprint here. The other motivation is the financial or the economic part, and basically this is also something which is important for the telecom operators, because when they deploy large networks, this energy consumption can be a huge cost for them. Even the 5G networks are 90% more efficient than 4G in the sense of transferred bits per joule. There is so-called rebound effect. So we expect huge increases in density and traffic of about 4 4.5 to 4 to 5 times compared to the 4G. And this is because we want more traffic, we want more coverage, we want more density, and so on and so on. So here I have some figures which are showing the network costs, and basically the energy costs are here according to this source estimated by 23%, but they differ for different network operators, and basically they vary from 20 to 40%, but already 23 or 25% are 1/4 of operating this network. And how this energy is distributed, we can see here. So basically the radio network is consuming like roughly 3/4 or 73%. Then we have the core network, which is consuming like 13%, the data center is 9%, and we have some other operation which is consuming like 5%. So the highest potential for optimization is basically in this area here, which is the radio network. So Big Green, what is the scope and objective? So basically Big Green wants to design and implement solutions to improve radio access energy efficiency. And we are pursuing different ways in these projects, which I'm not gonna go through all of them because it's too much to present in 20 minutes. But the thing is that first we want to introduce an intelligent plane where we use AI-assisted network functions, which would take care of the network efficiency. Then we want to implement efficient architectures for different baseband processing and radio function, like hardware acceleration, using specific instruction sets which can lead to energy efficiency improvement, and so on and so on. Then we use some relays, and we use some intelligence in the ORAN, where we use these relays in a relatively efficient way, where they can reduce the power consumption, and they can, for example, substitute some of the radio units. Then we have sensing assisted ORAN and beamwidth allocation. So basically we do sensing of the network, we see where the users are, and then we optimize the radio network based on that. And of course, this is an important topic. This is the RU energy consumption reduction, because the RU is actually one of the most power hungry element in this network. So we want to either substitute this RU with RIS where possible, or try to reduce the power consumption, especially in the power amplifier, so to say, and then improve network planning by enhanced spectrum resource allocation, energy transmission, and interference mitigation. And this is tightly connected with this part here, which is sensing assisted ORAN and beamwidth allocation. Mainly in this presentation, I would talk about this part of the project. Without extending the talk too much, I would just show shortly the architecture that we propose in order to improve the energy efficiency of the network, and what functions we try to address in the network to make it more energy efficient. So basically, we introduce this Big Green intelligent plane where we run our intelligent functions which gather different telemetry, sensing data, and so on and so on, and try to tune the network in a way that it's more energy efficient, or to optimize it for energy efficiency. That's one part that this project is working on. Then the second part is actually optimization here, where we try to optimize the DU and CU operation to be more efficient. So to use, for example, GPU optimization, or some special architectures which are used for energy efficient optimization, to try to implement the DU and CU on these architectures, and so on and so on. And then when we have the radio part of the network, so in the radio part we have the JCAS and RIS, and we have the radio access network where we try to optimize the RU. I think that already this thing was mentioned a few times, and I think that even the people who are not too much into this are already familiar, and therefore I would just shortly go through this part. So basically the integrated sensing and communication is the radar-like functionality added to the communication system. So, and the motivation is the hardware is already available. There would be minimally added complexity, and new services can be introduced with minimal cost. And there are many applications. Some are more realistic, some are more futuristic, so to say. They include like smart cities, smart traffic, smart home, object detection, classification, and property evaluation, like, for example, detect if it is vehicle, person, static obstacles, and so on and so on. Then we can do like environmental monitoring, like pollution, weather, vegetation, animal movement, and so on and so on. There are some biomedical and vital signs sensing, like heart rate, respiration rate, fall detection, and so on and so on. And this is all, and there are many other applications. What I want here to maybe also discuss is the types of combined communication and sensing that we are considering, let's say, in this project. So basically, the first systems which appeared were radar sensing systems where the radar was capable of sensing some data, let's say. Then we have a data transmission centric system, and we have like collocated system where we have collocated, for example, the sensing and the data communication systems. They do not share anything, and they are not really neither spectrum efficient, neither cost efficient. Then we have the coexisting systems where we have like the same hardware but separate waveform, and these systems are not spectrum efficient. And we have passive sensing where we use like the transmissions which are already there, but we just receive those reflections from these transmissions. And this is the problem with this approach, is that we cannot do much optimization. We must work with that what we have. And finally, we have the joint communication and sensing where we use the same hardware, the same waveform. We can do optimal waveform design. We have high spectrum efficiency. The cost is high cost efficiency because we share the hardware, and so on and so on. And this is the topic which we are basically dealing with. So how do we want to use the ISAC for improving the network efficiency? So with ISAC, we want to do sensing of spatial and temporal distribution and density of potential users. So basically, we have one radio unit which can sense where the users are, what is their density, where are the obstacles, and so on and so on. And then we can, based on that information, we can adjust the coverage respectively. So for example, when we have little users in that direction, where we can use some wide beams, which means less antennas, less active antennas, and in that case, less transmitted power, which means less capacity in that direction. But the thing is, we don't need it anymore, so we can adapt the power for this case. Or if we have densely distributed users, in that case, we can activate more antennas, and then we can increase the capacity and have better coverage and better capacity, let's say. Then we have dynamic resource management, which we can speak later. Then we can have sense-assisted file layer functions. For example, when we do beam training, we can use sensing data to see where the users are, and we can we can do this, for example, beam training in more efficient manner, and so on and so on. And then we want to combine RIS and ISAC, which I would mention in one of the following slides. So what dynamic resource management means is actually something similar to for example, a light bulb equipped with a movement sensor. So when user is moving towards the light bulb detects that there is a user, turns on, consumes energy. When the user is away, it turns off. That's it, does not consume energy and consumes very little energy. And the point is here that we want to do that on the network level. So with the sensing, we can generate heat maps where we sense where the users are during different periods of day, and we can activate different of these radio units. We can activate different radiation patterns and so on to have optimal coverage, and we can optimize for energy. So basically we apply this principle on a network scale. And even we can turn some of the radio units during night to save energy. We can increase the power of some radio unit to have bigger, let's say, coverage with the same capacity, and so on and so on. Regarding the RIS, so basically the RIS, as we already mentioned many times in this workshop, basically this is an almost passive device. So it's not really passive, but the power consumption of this RIS device is well below 1 watt. So we can say it's a few hundreds of milliwatts, and then 1 RU consumes like from 70, 80 watts and above, so to say. So the difference is like 1 to 2 orders of magnitude, or two orders of magnitude at least. And that's why we are interested in using the RIS. And the idea is actually to do sensing, to see if there are some obstacles, and to use the RIS in an efficient manner to go behind the corner or behind the obstacle in an efficient manner, and to know which RIS to use. Additionally, we want to implement sensing over RIS. So basically, the RIS should collaborate with the network in order to do sensing behind the obstacles and to detect if there are some users there, in order to see what's the most optimal strategy for energy efficient coverage of that area. So within the B-Green, actually, we developed a proof of concept system to demonstrate the ISAC and for its use for improving the network energy efficiency. What we did within this project, we evaluated, and we are working on development of different waveforms for sensing. We perform the signal processing, so we do the development of the signal processing for this sensing functionality. We work on detection and classification of objects and users, and we have proof of concept implementation of using software-defined radios for the sub-6 gigahertz band, and also we are working on a millimeter wave proof of concept in the 60 gigahertz band. And this is our joint communication and sensing, or ISAC system, which works in the sub-6 gigahertz band. So basically it's 1/n SIMO system. It can be also MIMO, but this is the minimal configuration which we need. The distance is estimated using time of flight. The angle of arrival is estimated by music, matrix, pencil, aspirate, or digital beamforming. In our case, we use digital beamforming because this is somehow the most simplest way that we can do. And the waveform which we use is wireless data transmission frame, which can be single carrier or FDM. So basically we have at least one transmitter, which is actually used to transmit the frame to the other entity. And we have the multiple receiver antennas, which are used for receiving the reflections and the frames which are incoming. And basically we use the AD converters to sample all this data and to generate multiple parallel beams in order to be able to estimate the direction of arrival. And this is our system, which is implemented using SDR. So basically we have a uniform linear array, which is connected to the SDR. So this is the receiver array, which is connected on the receiver side of the radios. This is the transmitter side. We have a load distribution, so the radios work in a full coherent operation. They are time synchronized by a so-called White Rabbit protocol, and they communicate with a PC in order to transfer the raw data which they get. So basically we are working in the 5 gigahertz ISM band, and the bandwidth which we have, like 200 megahertz. It's not too much. But as we can see from the next slide, we are able to detect a human moving in front of those antennas. So basically, this heat map, the node is actually here, the radio unit, and basically this is the angle, and this is the distance from the node. Maybe the offset here is not right, but basically this yellow dots represent actually the reflections which are coming from the user moving in front of the antennas. And we can see as the user moves, we can see that his position changes. Of course, the resolution is not the best which we can achieve, and it's not comparable to millimeter or terahertz systems, but for detecting a human is good enough. Finally, I'm wrapping up. So basically, BGreen addresses the use of ISAC for improving the network energy efficiency. An ISAC proof of concept is being developed, and it would be used later to demonstrate the fitness of this technology for improving the energy efficiency of the network. And the implemented proof of concept can easily detect potential users and their position. And future work would include demonstration of the potential for improving network energy efficiency. So thank you very much.
Thank you. And then please, for the attendees, please ask questions on the chat. We have one question so far, which relates to AI training, but that leads to high energy consumption. So the question is, how can AI be integrated into 6G while also meeting sustainability goals?
Yeah, so I mean, I'm not too much into this AI part, but I would try to answer this question. So yes, the AI training leads to high energy consumption, but I believe that this AI training can be performed, for example, once, and then this data can be later used on multiple occasions. And I think that this is what we are planning to do, so that we do not train the network. Of course, it should be retrained from time to time, but I believe the footprint would be minimal compared to the other part, because as I mentioned previously in this presentation, the main energy costs comes from the radio network. And if we go with another like pi here, where from the radio network, this comes from the power amplifier in the RU. So basically, this AI training would probably consume a few percent, maybe in the data centers or the core network, depending how we look at that. But still, the main part would be to optimize the radio network. So yeah, I agree. This would put a burden on this part, but I think that would not be the main power eater, so to say, for the network.
So I think in addition to the kind of energy consumption, at least in Hexa-X, they look at sustainability in a bit broader sense, considering like full life cycle analysis, like materials and how to deal with products after they've been used. So is this something that's also in the scope of the BGreen project?
No. Basically, we are addressing here mainly the radio network power consumption. So mainly here, and then we try to optimize like mainly the DU, which is consuming a lot of power, and the RU. And there we have achieved relatively good results by optimizing the power amplifier optimization and the DU processing. And of course, we want to improve that even more by turning off some of the RU devices using, for example, sensing and so on. But this life cycle management is not really a topic in this project at all.
Okay. There's one more question in the chat from Martin Beal. The question is, when sensing UV locations for deciding where to send beams, can you passively sense the UVs, or do you sense people holding UVs? Do the UVs actively send a signal to allow them to be sensed?
Yeah, so basically this is a good question, which maybe I didn't explain, but the idea here is to passively sense actually, for example, movement. and to basically sense where we have activity. And this would mean that probably there we expect the highest traffic demand, so to say. Of course, the same system can be used to sense possibly the position of the devices, let's say, but the idea here is to do deviceless sensing, so to say.
Oh, that's our timer for this presentation. Thank you, Vladica, for answering this question. Thank you for the presentation. We need to move on to the next presenter.